Okay, we're going to look at exam 2 of the fall 2018 semester for General Chemistry 1. This is basically covering the tail end of Chapter 3 through Chapter 5. So we're going to look at page 1 here. So question 1, 24 moles of methanol and 15 moles of oxygen combined in the given reaction below, and asks us to identify the limiting reagent and how much of the excess reagent remains. Now, there are, as with most of general chemistry problems, there are numerous ways to solve this type of limiting reagent problem. I'm only going to show you one method here. There are plenty of videos out there to kind of show you other methods. I'm only going to show you the way that I kind of approach these problems. And so to identify the limiting reagent, right, we have to remember what actually is a limiting reagent. And the limiting reagent is going to be the reagent which produces the least amount of product. Or it's the reagent that gets consumed first, right? It gets used up first as you're going through a reaction. Now remember, a limiting reagent can only be on this side of a chemical equation, right? It can only be on the left-hand side there. Those are our reagents, and over here in green, right, those are products. So if we're asking for limiting reagents, we're looking at the blues, and we're looking at what's in blue to see how much green gets formed. It does not matter what you're looking at, and here's what I mean. If we want to figure out the limiting reagent, whether it's methanol, right, we can see how much CO2 gets produced or how much water gets produced, and then compare that to how much CO2 or water gets produced from oxygen. It's not going to matter, right? All we want to do is see how much of the methanol, how much methanol produces how many products, and how much of the oxygen produces how much of the products. As long as you remain consistent in comparing CO2 or H2O, then you can get your answer from that, right? So here's what we're going to do. We're going to see how much methanol gets combusted to form how much CO2, and how much oxygen gets combusted to make CO2 also. But we could do it with water just as easily, okay? So let's put that idea into a mathematical equation. So here's how this looks, right? The problem tells us we have 24 moles of methanol, okay? We need to convert methanol, let me get my green pen here, we're going to convert methanol into CO2, okay? Now we're already in moles, so that makes this problem a little bit easier. So to convert methanol into moles, we know we have to have units of moles of methanol on the bottom and moles of CO2 on the top. Now I'm going to put some completely random arbitrary numbers. Oh my gosh, where did I get those 2's from? Our balanced chemical equation, right? Our stoichiometry. To convert units, we need some kind of converting ratio, right? We need some kind of stoichiometric ratio, and that comes from our balanced equation. So that's where that comes from, right? That's how I got those values. Right? So here's some pretty easy math, right? We multiply by 2 and we divide by 2, which tells us that we make 24 moles of CO2, okay? And I cannot stress this next part enough. Every time you do something to solve a problem, stop and ask, what does this mean? Okay, what does this mean? I just calculated that I have somewhere gotten 24 moles of CO2. What does that 24 moles of CO2 mean? It means that if I take 24 moles of methanol and react it completely, I will make 24 moles of CO2. The assumption that we make in this case is that we have excess oxygen around. The 24 CO2 here means that it comes from the 24 moles of methanol. All right, now we're going to do the same thing, but instead of methanol, we're going to do oxygen instead, okay? So the problem tells us we start out with 15 moles of oxygen, okay? we know we need to, whoops, I did this in green. Let me go back to green here. We have moles of O2 on the bottom, moles of CO2 on the top. We completely arbitrarily pick the numbers 3 and 2, right? 3 and 2. Looks like they're not that arbitrary, okay? You're converting one unit to another. We need some kind of conversion factor for that, some kind of ratio. And if we do this math, we multiply 2 and divide by 3, so we end up making 10 moles of O2. Oops, sorry. CO2. Okay. What does this mean, right? It means that if we take 15 moles of O2 and react it, we can make 10 moles of CO2. So if we start with our given amount of 15 moles of O2, we can make 10 moles of CO2. Now, what do these two numbers tell us? Well, remember, the limiting reagent produces the least amount of product. So 10 moles of CO2 is less than 24 moles. So the 10 moles comes from the limiting reagent. Here is our limiting reagent, right? Our limiting reagent is the O2. The 15 moles of O2 gets used up first. So we identified the limiting reagent, and there's our math to do it, right? All right, let me see if I can just square this off to give us some room to do the next part. Okay, how much of the excess reagent remains? Now the question's asking, okay, if I know my limiting reagent, my other stuff has to be the excess reagent, right? So the other stuff in this case is the methanol, right? So the question could have been asked, how many moles of methanol are needed to react with 15 moles of O2? And that's what we need to do, right? We need to compare moles of O2 to moles of methanol. So here's how that works, right? We're going to start out with 15 moles of O2. We use our stoichiometric ratio. I apologize, I'm running out of room here, right? For every 3 moles of O2, 2 moles of methanol. Okay. And this tells me 10 moles of methanol. Pause, ask the question, what does this 10 moles mean? It means that I need 10 moles of methanol to react with 15 moles of O2. Do I have 10 moles of methanol? Well, sure. In fact, I've got 24 of them. So how much of my excess reagent is left over? Well, I start out with 24 moles, right? And I need 10 moles to react. So 14 moles of methanol left over. Oops, remain. Let's try that again. Remain, there it is. So, as I've always mentioned with these limiting reagent problems, the math isn't too tricky as long as you have a balanced equation. The tricky part is asking yourself, what do the values mean? Like, what are the numbers that you're calculating actually mean? So always pause and ask yourself that question. And if you can't answer that question, that's kind of an indication to go back and study, right? Take a look, read through the chapter, whatever you need to do, okay? So our limiting reagent was O2, and we had 14 moles of the methanol remaining. All right, question 2. Adipic acid, and it gives us the formula there, right, is formed, right, from the following reaction, makes nylon, and ask us how many grams of C6H12 would you need to react if you want to form the 43.5 grams of adipic acid. And it gives us some very key important clues here, right? It says assume excess O2. Okay, so if you want to pause and read through this entire problem, I don't need to do that in the video here. This question tells us a couple of things, right? First of all, the very important flag that you should pay attention to is assuming excess whatever, right? Assume excess whatever. that makes this problem a little bit easier. That means if we know what the excess reagent is, we already know what the limiting reagent is. If O2 is the excess, then this guy over here is the limiting reagent. Okay? But here's kind of the twist to this problem, right? The twist to this problem is this. The problem tells us we want to make 43.5 grams of adipic acid, which is this guy here. We want to make that much. And then it says, well, how much of my starting material do I need? It's asking how much of my limiting reagent do I need to form that much adipic acid. So the math is completely different. It's never been seen before. No, I'm just kidding, right? It's exactly the same. We're just kind of working a little bit in reverse. Okay? There's one slight twist. We're starting in units of grams. We're going to have to convert grams into moles. Do a ratio to compare moles to moles, right? And then the unit that we want our answer is in grams, right? So we're going to have to do our grams to moles, moles to moles, moles back into grams sequence here. All right. If you kind of missed what I was saying there, right? Just pause, rewind it a little bit, and see if you can catch up, right? We have information about product. We're trying to find how much of our starting material we need. Okay, so we're starting with grams. It tells us that we want to make 43.5 grams of our acid. Excuse me for a second. I've got a cough. Sorry about that. So we need to convert grams of acid into moles of acid, right? That's our first step here, right? Grams into moles. I'm going to make the assumption that you guys can do that conversion. If not, check one of my previous videos or look up one of the videos on how to do gram to mole conversions. Okay. So in green, we're converting grams into moles. Let's pick black here, right? A mole to mole conversion. We are now in units of moles of acid. We need to convert it into moles of C6H12. Because that's what it says, right? And if you read the problem, it says how many grams of C6H12. We're going to use our stoichiometric ratios here, right? 2 to 2. And then, what color haven't we used here? I guess blue would be okay, right? And then moles back into grams. If you give me just a second, I ran out of room, so let me just move this down here. Okay. All right. Right, and then in blue, we're going to convert moles back into grams. So we have moles of C6H12 into grams of C6H12. Again, I'm working off the assumption that you guys can do these conversions. 84.16 is what I had. Right, and if we put together that math, I ended up with 25.05 grams of C6H12. So this is, question 2 was basically a reverse limiting reagent problem. Right? Pay attention to the terms excess. It tells us what the limiting and the excess reagent are. And then the other tricky part about this is just realizing that we're actually just working in reverse instead of in the forward direction like we did in problem number 1. Okie dokie. Question 3. So question 3 was just asking us to write complete and net ionic equations. It's a little bit trickier because I don't give you any of the chemical formulas, right? You guys have to remember what calcium chloride is and sodium carbonate and all this kind of stuff. Right? So again, I'm not going to cover naming in here. That was on the previous quizzes and chapter exams. So go take a peek at that. But let's go through it, right? So remember what we're dealing with here. Calcium chloride, in part A at least, calcium chloride and sodium carbonate are ionic compounds. And when you put an ionic compound into water, they're going to dissociate if they are soluble. Right? That's the assumption that we make for the first semester of general chemistry. Right? We make the assumption that all ionic compounds are soluble unless they are not soluble following the set of rules that we follow. Right? And if I zoom out here for just a second, let me scrolly. Right? And I gave you guys, where was it? Ah, there it is, right? And I gave you guys the solubility rules that we're using for this class. Right? So I'm not going to keep scrolling back and forth. This is in your notes, in the slides. This is also in your book. Right, so if you guys just want to refer back to this while I'm kind of working through this problem, there it is. Okay. So those are the rules that we need to answer this problem. Right. Remember, I will always give you guys those notes. It's not something that you guys, or excuse me, those rules. It's not something you guys have to memorize. Okay. So calcium chloride and sodium carbonate. So calcium chloride is CaCl2, right? And sodium carbonate is Na2CO3, right? Carbonate's one of our polyatomic ions. It's always got a 2- charge, so we need 2 sodiums with a 1+ charge to balance that out. Calcium's a group 2A metal, always has a +2 charge. Chlorine's one of our halogens, always got a -1 charge, right? So that's how we kind of balance all this stuff out. So we're going to take these and break them apart, right? So our complete ionic equation is where we take everything. Where we take everything that's in solution and write it as our in its ionic form. Right? There's 2 sodiums. Oops, that's a little bit redundant. We don't need to put the 1 there. I got a little bit too happy. All right. Now, in the complete ionic equation, right, we're mixing calcium chloride plus sodium carbonate. And remember, we have to ask what gets formed. Right? And behind the scenes, what we're doing is we split everything apart, and then we bring together new ion pairs. And here's what I mean by ion pairs. We're going to bring together the calcium and the carbonate. And we're going to bring together the chloride and the sodiums. Now, why would I bring those together? Why am I picking these very arbitrary, completely random ion pairs? Okay, well, they're not arbitrary and they're not random. Why am I picking the calcium and the carbonate in green? Well, calcium's a positive and carbonate's a negative. Positive and negative things want to come together, right? Coulombic attraction. And the chlorides and the sodiums are opposite, right? So they're going to come together. So we're going to pick ion pairs, oppositely charged ions, and bring them together and see if they're going to precipitate out based off of the rules that I was just talking about. And it just so happens that if you look at the rules, it says that salts with carbonate are generally insoluble. So if I bring, oops, I meant to do this in green. If I bring calcium together with carbonate, it will precipitate out as a solid. And pay very close attention to the charges, right? Always balance your charges. Carbonate's 2-, calcium's 2+, so all you need is 1 of each. Now, sodium and chloride. What happens if you bring sodium and chloride together? Well, they, in theory, would make, table salt, right? Sodium chloride. But our rules say that group 1A metals and halogens are going to be soluble. So if we have sodium and chloride floating around in solution, they're going to remain in solution. Well, that shouldn't be too much of a mystery. If you guys go out to the ocean, right, you don't see giant chunks of salt floating around in the ocean, right, because sodium chloride's dissolved, right? It remains as sodium and chloride. So the chloride just remains as chloride, and the sodium just remains as sodium. The individual ions floating around in solution. Got it? So step 1, let me see if I can find a nice color here, right? Step 1, I got the individual chemical formulas. Step 2, I broke apart both of my starting materials to make my individual ions, right? I made sure that everything was balanced still. If I had 2 chlorides, I better have 2 chlorides, right? 2 sodiums, 2 sodiums. Step 3, I brought together the new ion pairs. That's the red and the greens. And I checked those versus my solubility rules. Okay. Now a net ionic equation, I'm just going to clean up here a little bit. My net ionic equation is just basically what is the reaction that's happening? Right? What is the reaction that's happening? Well, here's what I mean. If you take a look at this over here, right, and take a look at this over here, the sodium and the chloride ions are not participating in the reaction. They're not doing anything. They're just floating around on both sides, right? They're just spectating, right? We would call them spectator ions. They're not participating in the reaction. Whereas the calcium and the carbonate are coming together to form a new compound and precipitating out. Another way of looking at this is that the chloride ions exist on both sides of the equation, right? And just like in mathematics, if we have something on both sides of an equation, we can cancel it out, right? And that's what we end up doing here. We end up canceling out our spectator ions, and what's left over is our net ionic equation. So let me write this in blue, right? We had our calcium, our carbonate, goes to make calcium carbonate. Okay. The other way of writing a net ionic equation is looking at what is the precipitant or what precipitates out and kind of working in reverse to break it apart, right? Either way is just fine. I prefer to go through the way that I did by identifying the spectator ions. That way we don't forget what spectator ions are. Just because we cancel them out doesn't mean they magically disappear, and it doesn't mean that they don't do anything, right? It's just they're not part of our net ionic equation. All right, so for part B, I'm going to work through this one a little bit quicker because we're following the exact same steps. I need to write out my starting material, sodium sulfate, barium bromide, right? Break everything apart. Make sure I have the correct charges for everything. Once I break everything apart, I'm bringing together ion pairs. I check barium sulfate is insoluble based off of our rules, but sodium bromide is soluble. Okay, and so there's my complete ionic equation. I identify what exists on both sides, and I cancel that out. Oops, I definitely didn't mean to do that. Okay, and what I have left over is my my net ionic. So barium, sulfate, goes to make barium sulfate as a solid. Done. Okay. I'm going to zoom out so you guys can see all of page 1 for this exam. And we'll stop this video here and we'll pick it up on page 2 next time. I don't know if I can stop it. All right.